everybody to the new COSI seminar series semester. Today, Carlos Jorquera, is that?
That's right, yes.
Carlos Jorquera from Boulder Imaging. He studied at MIT, he got a degree in physics and electrical engineering. He went on to work at NASA's JPL on imaging system for spacecraft and ground-based telescopes. And in 1995, he moved to Colorado and founded what is now Boulder Imaging, really close to here in Louisville. So, thank you for coming.
Thank you.
So here.
All right, so what I thought, the primary purpose of this talk is really to give you an overview of sensor technologies and digital recording technologies for scientific analysis in particular, for research applications. And as you probably all know, the proper choice of a sensor, it has a huge impact on the end result of your data. So that's why I'll spend a bit of time talking through that, because in today's market, everybo's familiar with megapixel cameras and broadcasting cameras, camcorders, and whatnot. At first look, they might all seem to be pretty similar in nature and properties. But if you look closely, you'll find that there are very distinct differences between cameras and sensor types that have a profound impact on the kind of data you're trying to capture. So let me go into that, and I'll begin by talking about sensor technologies in general. I'm focusing primarily on silicon here, so in the visible spectrum. Obviously, there are very specific sensors for infrared, but that's a whole different topic of conversation. The key areas of discussion here that I'll talk about that are the primary areas of comparison between cameras and sensors. Obviously, resolution, spatial resolution, sensitivity spectrally, as well as to the amount of light coming in. The architecture of the sensor plays a factor into how it operates, how it generates those images, and it also ties back to sensitivity and resolution as well. So I'll talk a little bit about that. Speed, meaning frame rate, how quickly you can freeze an event, those kind of issues are also very important. And data interfaces. As you'll see, there are many different types of data interfaces that have been developed over the years for many different applications, and each one has benefits and trade-offs. Finally, I'll close off with talking about high-performance digital video recording technologies, which is really the key focus of what Boulder Imaging is all about. Although we really, as a company, we integrate the full solution, so we go end-to-end. So if you ever have a need, you can come to a company like us and for example, how can I see through a bottle that is coated with a film and see the contents within it, for example, just to be for a silly example. But that's the kind of problems that come to us. So what is the right sensor, what's the right illumination for that problem, and ultimately what kind of system will integrate it all together into a solution. So let me go right into it. So in the imaging market, in terms of sources for cameras in particular and sensors in general, roughly speaking, we can divide it into three primary markets: broadcasting and digital cinema market, the surveillance and security market, and industrial and research market. The reason I group in this way is because their needs and requirements and motivations are quite different. Broadcasting and digital cinema is all about how beautiful the imagery looks. And I'm simplifying, of course, to some degree, but you got to keep that in mind because it is a very important consideration. So long as the imagery looks pleasing to the human eye, that satisfies that requirement. So you're able to make certain trade-offs, particularly when it comes to bandwidth and transmission of that data. For example, compression. Compression is regarded as completely acceptable today in the broadcasting industry, which is not acceptable for most scientific applications. Surveillance and security, some of the key needs and motivations are to mass produce them so that you can provide for wide-scale coverage of sensors. So cost is paramount in that industry. Low-cost sensors, and typically the trade-off is for the quality of the technology, either image quality or data content quality. Industrial inspection and research applications, the focus is really about the data, the quantitative content of that data, not just qualitative. Now it's quantitative. Can you really believe that particular projectile is moving at 1,500 miles per hour plus or minus, a tenth of a mile per hour? To believe that, you have to really believe in that data. So like I said, I'll talk about some of the key properties of sensors and camera technologies. Start with resolution, of course, which really determines the ability to, what is the smallest feature you are able to detect or sense in a scene. This, of course, obviously is dictated by the number of pixels, horizontally and vertically. What's interesting to keep in mind here is that in terms of broadcasting and surveillance type cameras, those cameras that must comply to certain predefined standards, like NTSC or the SMPTE standards, the formats, meaning the number of pixels and the geometry of those pixels, are dictated by those standards. So you can't just pick any resolution you want. It just won't come that way. They come in standard definition, 640 by 480 typically, or HD formats, which would be 1280 by 720 or 1920 by 1080, or well, basically those. I mean, those are the predominant formats. Pixel layout, of course, is also important when it comes to resolution, and I'll talk next about specifically what I mean about that. And color format. The reason color format affects your resolution is that most sensors today, cost-effective sensors today, use a filter pattern that gives you the full color content, the red, green, blue components, but they're not independent pixel by pixel. They have to be interpolated from near neighbor pixels. So therefore, your color resolution is compromised, as opposed to a monochrome image that each pixel contains an independent value, spatially independent from the adjacent pixel. Like I was saying before, this is some examples of what's currently available in the industry in terms of sensor technologies. And of course, this is always evolving. So this is in terms of what I checked on semi-recently. Of course, HD formats, you have 720 and 1080 are very commonplace today. You'll find them in a consumer-grade camcorder at video rates of 30 to 60 hertz. In the industrial market, you'll find much bigger sensors, or even in the digital cinema market, you'll find bigger sensors that are in the 4K or larger format. But to give you an example, when you combine high resolution with frame rate, you start to get to very high data rates. And so the number of choices out there are fairly limited. Salvador Imaging is a company that traditionally specialized in building pretty high-end sensors, well, cameras out of high-end sensors. And one of the largest format cameras at video rates was this one at 4K by 4K pixels, 30 frames per second, with 12-bit dynamic range. In terms of really high speed, however, what you find is that there's specialized cameras designed for that purpose. The fastest one I know of today at megapixel resolution is it's a Photron camera that can run 7,000 frames per second. If you calculate that out, you'll see that data rates are in the many gigabytes per second of throughput, extremely high data rates. Higher resolution sensors are currently available up to 100 or 100 plus megapixels. They're primarily meant for digital photography applications or very specialized remote sensing applications, like like people that use like Google Earth, for example, or QuickSat, QuickBird, they use specialized sensors like that. Sensor manufacturers like Dowsa, Kodak, and Fuji specialize in making really high-end sensors for those applications. Earlier I mentioned pixel layout affecting resolution. What I meant was this, is that conventional CCDs have a very much a rectangular type of layout of pixels. They are spaced horizontally and vertically in a grid, essentially. Fuji came out with this very interesting concept of essentially turning that layout 45 degrees, which results in much higher resolution horizontally and vertically than if you compare it to this layout. And even further than that, they claim that you can double your resolution or quadruple, or if you're talking about just pixels, by interpolating between a set of pixels. Although that might be questionable in terms of what you get out of it. Going back to color resolution and ways to do that, one approach taken by a company called Foveon is to actually provide an architecture where you can get all three color components within one unit cell, within the pixel unit cell. They're not actually spatially vertically positioned, but it's actually a buried channel within silicon. But in any case, the concept here is that shorter wavelength light is absorbed at the much shorter, well, let me back up. The longer wavelength light penetrates much deeper into the material than shorter wavelength light. So using that concept, you can actually discriminate the various colors by the depth by which it penetrates the silicon. And thereby, you get full color content per pixel. However, there are some limitations to that. You actually do get a fair amount of color crosstalk between the color channels, as opposed to other designs like 3CCDs we mentioned a little later here. The more commonplace form of doing color imaging is mosaic, using color mosaic like I talked about before, where you have individual filters, pixel by pixel, that alternate. You have a line that has, for example, the green, red, green, red, green, red, and the next line will have blue, blue, green, blue, green, blue, green. And you can interpolate for all three color components by looking at the adjacent pixels. And that's what you commonly find in virtually all commercial grade cameras out there, broadcasting cameras to a large degree as well. It's a much more affordable approach than going with 3CCD technology, where you actually take three sensors, made them to essentially a prism, and thereby you form three separate color images of the same scene. As you can imagine, that's a lot more complex, more expensive to build, requires specialized optics, and has a lot of cost trade-off issues. There are also a number of other mosaic patterns out there that use different color components, and they're suited for different kind of applications that use, this kind of color scheme is primarily used in the printing industry, but it applies for photography as well. And going back to 3CCD cameras that you might find out there, there's a number in the industrial market that are available, which will provide you the full three color components per pixel. However, the vast majority of the 3CCD cameras are in the broadcasting industry, and those actually output 422 encoding, which what it really means is that for every 4 pixels you get 4 luminance values, essentially intensity values, and you only get 2 components per each color, essentially chrominance value. So what that really means is that your color components are subsampled. So although it's a 3CCD, you don't actually get the full value from a broadcasting camera. 2CCD sensors are 2CCD cameras are much more rare, where you have one main sensor that's capturing the luminance information, the intensity information of the scene, and the second sensor is the color mosaic and provides the color components. The reason why that makes a lot of sense is that that's, you know, that's pretty much how the human eye really operates. So it really matches human color perception quite well. Human eye it's much more attuned to monochrome or intensity variations than it is to color variations. Spatial variations, I mean. Let me talk about a couple applications here and to demonstrate why these factors really matter. GE, who makes wind turbines, actually they bought this operation from a German company, but anyway, that's beside the point. They make wind turbines now. They came to us looking for solutions for how to characterize the kinematics of their blades, essentially looking at how the blade deflects and twists as a function of wind velocity. That's really important to them because that really affects the efficiency of the blade, obviously. And it also allows them to operate that wind turbine through a whole range of wind speeds. So typically, at very high wind speeds, you have to shut down the turbine so you don't overdrive the system. With this new blade design, which I'll show you in the next slide, actually, this is actually not a new, this is a more conventional design, straight blade. With the new design, it's made in such a way that the composite materials will flex and twist when the wind gets too strong and come back to full capacity when the winds slow down. Anyway, the point of all this is that they needed to measure deflection and twist on the surface of these blades, which are about 150 feet, 50 feet in length, 55 meters in length, not 50 feet. Well, they range 30 to 50 meters in length per blade, and they wanted to measure the deflection and twist to an accuracy of a millimeter in free space and twist to a tenth of a degree accuracy. If you look at, if you think about the scales involved here, you can quickly imagine why high resolution camera is very important for that kind of measurement. Turned out that we can constrain the problem to some degree so that a 4 megapixel camera with this resolution here was sufficient to capture the data we required to make those calculations, which were accurate actually to less than a millimeter in measurement. But let me show you what I'm talking about here. So this is a section of that new blade design that you're seeing about 2/3 of the blade length here. And you can see a number of things going on here. You can see the imagery in the background, how much the lighting varies as the blade spins up. Oh yeah, I should back up a little bit. The camera is actually mounted at the hub of the turbine, looking down or up the surface of that blade. So when it looks up into the sky, it gets reflection, it gets direct light from the sky. When it looks downwards, it gets obviously scenery from the ground, which is a lot darker. There's the variation is several orders of magnitude. Well, no, not quite, but it's a very dramatic difference, as you can see from the imagery. Although that video was playing fairly slow there, it really was running at 60 frames per second to make the measurements thereafter. So what's going on here is we're capturing the imagery, and you only see, of course, a compressed version of the full data set. And we placed markers at locations of importance to the measurements they're trying to make on that blade, so that we can track their motion in space. And as the blade moves, we are able to measure where the location of those markers, and also fit them to a model which is referenced to a rest location, so that we can discriminate between what's a real marker as opposed to a false detection, which down here is a false detection. Eventually leading to the actual measurements that are going on here. The two-step approach of processing, one is just simple, essentially blob detection. You detect for these markers, and then secondly apply it to a physical model of what the configuration should be, allows you a great power to discriminate valid measurements from false detections. Going back to sensitivity, Spectral sensitivity obviously is very important for choosing a sensor. And of course, it's very much tied into what you're trying to detect. Factors that play into that and how you measure the sensitivity of a sensor is primarily quantum efficiency or responsivity. They mean roughly the same thing, although they're very different quantities. Quantum efficiency is essentially the percentage of photons that are detected. So 100% quantum efficiency would be a perfect detector. Responsivity is more of it's really a measure of the response to power, really. So so if you look at a perfect 100% QE curve, you actually would see a ramp, not a straight line curve. Just something to be aware of. Spectral response is a strong factor, of course, of the design of the sensor, particularly the composition of the unicell, the pixel makeup. In going back to some of the things I mentioned before with the Foveon sensor, the surface effects, things that are happening at the very top layers of the material, have the most effect on shorter wavelength photons, while longer wavelengths into the red, they penetrate much deeper into the material. So what's going on back here plays a bigger role in the very long, near infrared type of wavelengths. This example here shows the makeup of a typical photodiode cell, which you typically find in an interline transfer CCD type of architecture. And I'll show you a few other examples and the various trade-offs between other different architectures. But first, let me talk about spectral sensitivity and how it plays a role in certain applications. In this example, we're looking at laser beams from fighter aircraft, F-16s or F-22s, essentially targeting lasers that lock in on a ground target, and of course the weapon system will then follow that signature that's being projected by the laser. Our system is designed to do is to really detect the presence of those laser bursts, which occur in unknown intervals. So we have to measure that interval. And each laser flash only lasts in the order of 10 to 20 nanoseconds. So you can imagine that's a little tricky to do. Ultimately, what they're looking for is the correlation between two targeting laser systems. Obviously, the more sophisticated your signature is on that target, the less likely it is for the enemies to try to duplicate it, and of course, and project that same signature on the friendly on our people. The military goes to great lengths to make this very difficult to recreate. In this particular application, it's a dual beam near-infrared laser targeting system, and we measure through using near-infrared filtering systems and an in-gas sensor, which is obviously not silicon-based, but it's particularly designed for near-infrared wavelengths up to about 1.7 microns. It's designed particularly for that high energy, relatively high energy infrared part of the spectrum. And we're able to detect each individual beam by using a specifically targeted narrowband filter. And by using a collection of 4 toll sensors, 2 very high-speed sensors to detect the presence of the beam, and 2 imaging systems, 2 imaging cameras really, that are synchronized to the detection sensors, we're able to capture both temporal information about the beams, which essentially the pulse duration, the frequency, the jitter, power distribution, and the beam distribution over the target, and of course the correlation of the 2 beams together. This image really represents a fusion of all the sensors into one final image, because they're all independent sensors that are capturing this. Going back to sensitivity, I put this in here to point out, to make an important point about choosing sensors, and that is that unless you really require color images, that for whatever reasons you must see color, the rule of thumb is really to go with a monochrome sensor. And the reason is that it should be fairly obvious that as soon as you put a filter, you're cutting out a huge amount of the incoming illumination that's entering your light path. And so if you don't care about color information, you're cutting away a lot of your sensitivity of that sensor. Typically, as a rule of thumb, it's roughly 2 f-stops, so a factor of 4. Going back to sensitivity, another important considerations that might or may not be obvious depending on your field here. Pixel size. For everything else being equal, if you're trying to see an object or a scene of a given size, the bigger the pixel you use, the more light you're going to get integrated into that pixel. And therefore, the more sensitive that sensor will be. The pixel size does impact directly the size of the lens, so that can be very detrimental if you're very far from your scene or your object. It also impacts dynamic range. Dynamic range is a strong function, or almost directly proportional to the pixel size, really, because the pixel size detects the size of your well underneath it. Fill factor is a metric used to define how much of the area within a pixel, a unit cell, actually is sensitive to incoming light. And for typical sensors like interline transfer CCDs or CMOS sensors, that fill factor is typically less than 40%. To compensate for that, most manufacturers of sensors put a micro lens that covers the full area and then projects the incoming light into the photosensitive area of the underlying pixel area, the underlying area of the pixel. Dynamic range is back to other factors that affect sensitivity. Obviously, random noise floor. Your random noise is ultimately going to dictate what is the faintest object or scene you're trying to see or detect. Dynamic range gives you a measure of essentially a ratio of maximum signal to the RMS noise floor. So it's a very important metric to use in picking the right sensor. Typically it's given in decibels. Just because the camera says it's, for example, 12 bits, doesn't really mean that you have 4096 of dynamic range. You're not going to get all those pixels actually being useful. Some number of those pixels are lost in the noise. Typically, for broadcast cameras, all you get is maximum of 10 bits, so you're just going to be always less than 1,000 to 1 for dynamic range. For scientific grade cameras, you can get close to 16-bit, but not quite. Depends on the sensor type. Here's an application where dynamic range is very, very important. It's actually an application that's, I think, just down the street from here. Professor Criminaldi's lab involved in fluid analysis work, where they illuminate photoluminescent chemicals within their big tanks of water, and they're looking at flow, the various interaction of the chemicals and flow analysis. And that's a crayfish right there. What's really interesting, the research they were doing is they were trying to characterize and try to understand how certain species of crayfish are so efficient at tracking minute amounts of chemicals through very large volumes of water. So our system, the system we helped them develop, involved multiple cameras, two simultaneous cameras that provided two bands of narrow band imaging to look at two different chemicals simultaneously, and a third camera that actually tracked the motion of that crayfish, so that it moved the cameras right in front of the creature. Why dynamic range was important here is because typically with laser illumination, particularly in environments where you get a lot of reflections like water, you can get huge variations in dynamic range, very dark areas right next to very bright areas. So in this case, they're using 12-bit cameras that give them very close to the full dynamic range that's possible. Now let's see, I don't know how I'm doing with time here, but go real quickly through some. Doing all right? Okay. I'll go quickly to some sensor architectures, and the reason I'm doing this is because it gives you a feel for some of the trade-offs that are possible and why you might choose one versus another, and why picking a sensor is not so straightforward as it might appear. Full-frame arrays are what most people might consider the traditional CCD, where it just simply consists of individual unit cells that shift down to a horizontal shift register, and that reads out through an output amplifier. So in this design, the full unit cell, the full pixel, is sensitive to light. So you get 100% fill factor, or extremely close to that anyway. Typically, you see this in very large format sensors, like in photography applications, where you want very high pixel counts, you want high sensitivity, there's no light loss, there's no gaps in here. However, that's not throughout the whole spectrum. Because there's polysilicon electrodes over each pixel, the short wavelengths are actually primarily lost, but it's very sensitive throughout the rest of the spectrum. The biggest problem with this architecture is the shuttering mechanism. It really has no shutter, meaning that there's no built-in shutter to the actual readout. So when you're reading out, shifting down these lines, which happens one at a time, the pixels are always looking, they're always seeing light, they're always staring. So unless you have some sort of mechanical shutter, you're going to get severe smearing in the image, which makes them unsuitable for many applications. But where you have an application, particularly where you control the duration of your lighting, like with pulse illumination, like lasers or LEDs, this works just great. It gives you a lot of sensitivity and very high pixel counts. Frame transfer CCDs is a variation of the same concept, where you have the same layout up here, but you have a storage location, essentially where you can very rapidly shift down the contents of the pixels down to the storage area, which is not sensitive to light. So the trick here is that you have to do this quickly enough so that to minimize any smearing. So if the time it takes to shift is anywhere near your exposure time, then this will not work. You get very significant smearing. But if your exposure times are long compared to your shift time, then you get pretty crisp images. Again, the benefits: high sensitivity, same as before, 100% fill factor. But again, for short exposure times, you will run into smearing issues. Interline transfer CCDs, which is probably by far the most common architecture out there, or slight variations from this, involve the design where you have photodiode cells which shift the integrated charge into a vertical shift register, which is shielded from light. And so that the concept here is that you shift all of this in one instant. Well, typically takes, in the order of, depending on the design, it can take some finite amount of time, but it's very short in nature. So what this allows you to do now, of course, is that it no longer is a situation where you're always being exposed to light. You quickly shift over, and now you're ready to expose the next frame. So all the smearing issues go away, unless, of course, you get saturation issues where you start blooming. But there's mechanisms to work around that issue, and Dave can answer any of those questions if you have them. So let's see here. the basic unicell looks roughly like this. Again, the vertical shift register gates are right next to the active area. And typically you would have a micro lens over the whole area that then will refocus the incoming light into the area that's sensitive to light. Going back to a very important point, this has built-in electronic shutter down to microseconds. So you can really make use of the sensor at very short type speed, very short exposure times, which makes it obviously much more useful. CMOS sensors, of course, are what's becoming the most popular sensor out there today. It's fundamentally a very different design. It really incorporates a multiplexer readout layout, which makes every pixel addressable. The pixel circuitry itself incorporates charge to voltage conversion. There's row selection, reset, and depending on how much room you have in there, you can incorporate some other more sophisticated circuitry to do compensation or correction for non-uniformities, things of that nature. You can also incorporate the analog to digital converter right on the chip, which makes it very convenient. A fully digital solution right out of the chip. Leveraging off the CMOS foundry, of course, you can make use of the ability to get down to very small pixel sizes, down to a micron, which is typically what you find in this kind of phone cameras and so on, where you can really fit megapixel resolution in an extremely small area. Of course, when you do that, there are many trade-offs. I mean, when you get to that small of a size, your dynamic range goes down the toilet. They have, the readout, because of the readout architecture, you have control of shuttering down to microseconds or even nanoseconds, depending on the design, which makes them very useful for particular high-speed applications. Some of the early architectures, which incorporated essentially three transistors or equivalent to transistors per unicell, didn't have a way to reset globally, meaning to start and stop exposures for all pixels simultaneously. So you ended up with a mechanism called rolling shutter, which essentially exposes, essentially as you read out the lines, you start a new exposure. So you have the top lines exposing earlier than the bottom lines of that sensor, and which leads to very funky artifacts. I'll show you a little later here. Low fill factor. There's a lot of transistors in there doing lots more than just detecting light. Obviously, again, you can use micro lenses to compensate for that. Very fast readout. That's one of the main reasons why you go to CMOS, and of course, cost is another one. Let me talk a little bit about speed. So there's two ways to look at speed: freezing motion and slowing down motion, so that you can see how it flows at a slow down rate, essentially. So exposure control will freeze the motion, and frame rate will give you the continuous flow of that motion. So two very important considerations when choosing a camera or sensor. So if you're involved in high-speed imaging, you got to really worry about exposure control. Can the camera really get you down to a microsecond exposure time? Can it really control it to that level? Not many cameras can. That's a very select few can really get you a crisp image down to a microsecond, and even fewer yet can go down to 200 nanoseconds. And for some applications, that's absolutely necessary. I mean, for ballistics imaging applications where you got to be down in the 400 nanosecond to really freeze the motion of the projectile, that becomes very critical. other considerations, of course, that go with that is the exposure accuracy. Is it, is it really 2 microseconds or is it 2.3 or whatever? That's camera dependent. Jitter variations in the exposure control. Is the camera able to expose while it's reading out? What that really means is that some cameras, it's much easier to build a piece of electronics that will read out the sensor and then begin the next exposure. And while it's exposing, it's not reading out. That directly impacts your frame rate. So while you expose, you cannot be reading out the previous frame. Therefore, you have to wait. So that's an important consideration that's not obvious from looking at a data sheet from a manual. Also important synchronization to other events if you're looking at multiple sensors. I mentioned before the electronic shutter mechanisms and the issue with rolling shutter. Here's one of the artifacts you can see in rolling shutter where you can see this warping effects. And it's exactly due to that mechanism. In fact, I think the early iPhone camera had the same issue where if you moved a little too much, you would get some weird warping effects. Global shutters are designed to start and stop exposure in all pixels simultaneously. So obviously very important for high-speed imaging. Most CCDs, the vast majority of CCDs will support that by default. And modern CMOS, particularly the cameras we use, all are 4 transistors or more in composition, which incorporates the global shutter mechanism. Frame rate, in terms of high-speed cameras, CMOS sensors are what you're going to find to be the most popular choice for high-speed imaging. Again, the reason was for the readout architecture and the way you can control exposure times. Traditionally, when you get to thousands of frames per second or hundreds of thousands per second, even 1,000,000 frames per second in some few cases, those cameras have been restricted to memory-based cameras, meaning that they did all the recording internally to some localized memory within that camera head. That constrained you to recordings that are very short in duration, typically no more than a second or 2, depending on your rates. Today, however, we have a number of cameras available that are maybe not quite as fast, but fairly close, that are industrial quality CMOS cameras from people like Microtron, Basel, or Photon Focus cameras that we deal with all the time, that provide megapixel resolution at frame rates of 500 frames per second and above. And if you do windowing, which of course CMOS is very well suited to do, you can get hundreds of thousands of frames per second. Windowing meaning you only read out a certain section of that sensor. What this allows you to do, well, not directly, but because the camera now is actually streaming the video out at those rates, you can plug it into a suitable system that's fast enough and then record for extended periods of time, almost unlimited in duration, if the system can keep up. And of course, our systems can. That is, that really breaks that paradigm that existed with memory-based cameras. That if you're doing high-speed imaging, all you could do is 1 second. That was, the accepted norm in the industry. Let me just talk lastly about interfaces. I want to go really quickly to this, so I don't run out of time. There's a wide range of interfaces out there. Of course, historically, we had NTSC, RS-170, PAL, of course, the most common interfaces in the TV industry and broadcasting industry. Long history there, obviously. S-Video made improvements on the quality of the color video by separating the chroma and luminance components. And I mentioned RGB VGA here because it's another way of sending out high definition, high resolution color video like your monitor does. But some cameras actually use that as a means to output data. Digital interfaces, you'll find a wide range of standards and not so standards out there. Parallel LVDS was predominant only just 7 years ago or so, and nowadays you find camera link that's really united the camera industry into much more of a standardized ways of outputting and interfacing to a camera, outputting data and interfacing to that camera. Geeky Vision, it's relatively speaking, more of a newer standard that's been it's now pretty solidified in the industry, very predominant in many areas. IEEE FireWire, 1394 is FireWire interfaces. HoundLink is useful because it has a very low conductor count. Just a pair of wires will give you up to 300 megabits per second, which is highly desirable for applications where you might have a gimbal set up where you have to spin all around and you don't have a direct wire connection to the camera. SDI is similar in that regard. It comes from the broadcasting industry. HD SDI is improvement on that standard to give you high resolutions. Either one of those can go over fiber as well, and you have separate from that, it's fiber channel audio video, which is more of an avionics standard, and with ARINC at 18 is being used by people like Airbus and Boeing and a lot of their aircraft avionics equipment for transmitting video and audio and other telemetry. Let's see, this can get real boring real quick unless you're really into this sort of thing. So I'll go very quickly unless you have a specific question. But what's good to know about camera link is that it's really it's a point-to-point connection, very fast, very efficient, low latency. Oh, okay. Oh, so I better just skim through here. Geeky Vision, it just leverages of the Geeky technology. And therefore it's very convenient, but it still is, it should be looked at as a point-to-point connection for the most part. You can network multiple cameras so long as they fit within the bandwidth, and that's not necessarily a given. So that's why I said it's safer to look at it as a point-to-point type of interface. SDI, it's coax based, but it's digital. It's a fully digital interface. That has been expanded to handle high data rates, 3 gigabits per second, and the latest incantation of the standard. Let me skip through that. And of course, let me spend a little time on what we do primarily, which is high performance video recording. So a key focus of what we do is building systems that are agnostics to data inputs. So of all the cameras I talked about, sensor types, no matter which one you pick and choose, you plug in one of our systems and you're guaranteed to get every single bit from every frame, from every camera, every time. And yes, that is a slogan we use. So essentially, we're trying to do is give you total confidence on that data set. There's no compression, there's no bits lost ever. Like I said, input agnostics, a key focus of what we do. The ability to simultaneously capture video from multiple streams. To do this is non-trivial. It requires if you start to combining high-res cameras with high-speed cameras, it quickly can reach data rates that exceed gigabytes per second. This example here shows you 1.5 gigabytes per second of video, although keep in mind it's coming from a laptop, so it's been highly compressed, so I can show it to you. But the source data came from a collection of 4 cameras, running at 500 frames per second here, 300 here, 60 here, and 100 here. These are HD type of resolutions. This camera alone generated 650 megabytes per second, and all synchronized, time correlated to microsecond level accuracy. Our systems can do that because they can handle data rates that can exceed 1400 megabytes per second, and that's really 1.4 gigabytes per second, either from one source or from multiple simultaneous sources. And recording speed, it's varying on number, type, format of inputs, like I've been mentioning before. And this goes a little bit more into detail. All that performance is all going on really in the background. You have a system that really works more or less like a high-end VCR. You have always access to your video. You never lose sight of what the cameras are generating, which is very important for a lot of applications. Playback is immediate. There's no delay whatsoever. You press the stop button and you have access to all your data immediately. And I'm talking about terabytes upon terabytes of information that you can scan through dynamically to any moment in time from all your sources. Obviously giving you a lot of power to analyze an event. People like NASA or the Army, the military, they eat this stuff up. But as you can probably imagine, it's non-trivial to do. Furthermore, one of the things that is really unique to us is that we couple, and I only mentioned a few things here, but we couple the ability to not only capture all that data, record it, time correlate it, and store it, and make it fully accessible, but also we can incorporate real-time processing modules that can run as you're capturing your data as it's coming in to do all kinds of processing. Things that are just real, straightforward things like non-uniformity correction, Bayer color interpolation, background subtraction, things of that nature, but much more advanced things beyond that allow you to do things like this. Ice crystal detection and characterization on the fly as the aircraft is flying through clouds. This is research we do in collaboration with SPEC out of North Boulder here for NCAR and NSF. And for Lexmark, let me go back up. These cylinders are printer drums that go in laser printers. We inspect 100% of the product they make, looking for surface defects on those printer drums. And these defects can generate defects on the printed page. So obviously it's very critical that we find every minute feature down to 15 microns in size within the surface of a printer drum. And just to close off, another key feature set that makes our systems very powerful is their scalability. The ability to essentially network any number of these systems together to expand endlessly the number of inputs or data rates that can be supported for recording. With very flexible interfaces to allow quick integration into systems that we don't control, like from our customers. Just to close off here, as you've seen, there's a huge number of sensor and camera combinations possible out there in the market. The many trade-offs between them. Each has unique capabilities that make them very well suited for particular type of detection applications. And what we think we provide to the picture is the ability to allow our end users to just pick and choose the camera they want, and they'll be guaranteed to plug it into a system and it's just going to work. Whether it's 12-bit, 16-bit, 16 bits for color, false color, whatever it might be, is supported by our system. That provides what we call the universal approach to video recording. It greatly minimizes complexity when it comes to sensor selection, camera choices. It also provides long-term value, and certainly the ability to support multiple inputs simultaneously allows for much more efficient and analysis and quick conclusions from the data sets that are being captured. So, any questions?
So we have time now for questions.
Okay. Oh yeah, we also have some handouts here if anyone's interested. Include some information about the kind of work we do and a white paper on technology that we produce. So anyone wants them.
I'll put some down on that end too.
And we are hiring, by the way, so please talk to us if you're looking.
I have a question regarding, it was one of your final examples, and it was basically defect detection. And earlier you gave an example of how that went around, but people want to know every single defect in their product, essentially, right? They don't want anything to pass and go out there and then cause a fail. And you sort of insinuated that you have the ability to detect 100% of these defects. And I'm just curious if that is true, and if you also have a pretty high false positive detection then as well. Are people biased in favor of that now? That they they want to be bothered with everything instead of just.
Okay, just to answer the first part of that, for environments where you're able to constrain the problem to some degree, like printer drums, for example, you can constrain that problem relatively well. Although what you cannot control is the actual process. What's going on with that? You take a cylinder made out of aluminum, they diamond turn it for a smooth finish, then they anodize that, and then they coat it with multiple layers of photoconductive material. That whole process can vary a lot from run to run, depending on how hot the machines are running, or the chemical composition. Obviously, all those many variables. So, what am I getting at is that prior to us, they had a different machine vision system in place, running. This is actually the Boulder facility up north here, and they were getting a lot of false positives. To a level that it was better than inspecting it by hand, which originally that's how they inspected the parts. So it was an improvement in terms of labor and number of defects that got through, but they still got a lot that went through. They had the problem of false positive, which results in a lot of extra work to screen those out, right? They also had the problem of failed detections that went through and it made it to the printer, and now the printer has to be reworked. A lot of wasted energy there and effort. The reason they came to us is because they wanted to solve all those problems, and we did. That plant operates to the point now that they measure the defects they find are no longer traceable to their process in general. They're traced back to the actual materials. They go to the aluminum core provider and say, hey, all these defects come from you guys. You got to fix this. And so they have to buy our system, which is great for us. But my point is that we got into a level where we can really guarantee extremely high detectability and very low false detection rates. And that makes it an extremely powerful tool. Without that, it isn't. If you can't trust the tool, then you can never get to the level that you say nothing is ever going to sneak through. So you got to get to that level. And that's not trivial. It's very difficult. And by the way, it used to be Cognex in there. So we kicked them out. Yeah.
Earlier in the presentation, you were talking about color sensors a little bit, and you were talking about the Bayer filters, really common, and then like the Foveon approach and stuff like that. And is there such a thing as an ideal color imager?
It depends what you're trying to image. The color mosaic was really ideally designed to mimic the human eye or the human color perception, and it's really well tuned for that. So it's generally well accepted in even in the entertainment industry. Well, unless it depends who you ask. I mean, like Spielberg will never use them, but many others will. So it really depends what you're trying to detect. So if you're trying to please the human eye, then those are pretty darn close. Especially if you marry it to a full resolution monochrome sensor that gives you the full resolution, then the imagery is you can't tell any missing color resolution with your eye. But for scientific purposes, say you're trying to track a missile, 10 miles away and only 3 pixels across. If you have a mosaic pattern, you're going to get all sorts of artifacts on the edges.
Second part of that, I think, is do people ever try within the visible band having imagers that are sensitive to more than 3 colors?
Yes, it's been done in a number of applications, and particularly where I've seen them is in the food industry. In the food industry, where you're trying to detect for mold or things of that nature, and there's some subtle color differences that typically benefit from that approach. Although I haven't seen commercially applied really, but for specific applications like that, yeah, I've seen it where there's more than 3 filters used. Have you seen?
Yeah. It really is color gamut is a real issue.
Yeah.
3
color point slips, well, satisfies the bang 9.9% case.
Right, right. Of course, that depends which bands you pick and how much they're decoupled relative to each other, to whether or not you can truly, I mean, mathematically speaking, you can truly represent every possible color combination.
So, how fast do you, your system image the spinning turbines? And is the goal there to, study the working reflections for, folks that design these things, or is there a feedback, or, is the goal to have a feedback system where you adjust these turbines as, keep them more efficient?
That was done at 60 hertz, so 60, well, the camera was running 60 frames per second, so we're taking 60 measurements per second. And it was intended for the actual design lab blade, so it was the first article ever made, and they were trying to see whether it met the design specifications. It's, as of yet, it hasn't been taken to the level where it provides some sort of feedback loop. Of course, we'd love to go there. We like a system in every turbine out there, but they haven't adopted it yet.